One last connection I'd like to highlight is the connection with Taylor series and the derivative of the original function. So we've actually seen this before when we talked about Taylor polynomials. So I'll start with an example to recap that, but then we can extend it to a similar idea with knowing the Taylor series for a function. So if I said that the 11th degree Taylor polynomial of the function f of x equals 2x divided by 2 minus x squared, centered at x equals 0, is the following. T sub 11 of x is equal to x plus x cubed divided by 2 minus x to the 5th over 4 plus x to the 7th over 8 minus x to the 9th over 16 plus x to the 11th over 32. So it turns out this is a true statement. This is the 11th degree Taylor polynomial centered at 0 for this given function f of x. Then we could answer a few questions simply from having the information of this Taylor polynomial. First of all, find the 9th derivative of the function f of x centered at 0. Of course, one way to do this is to simply take 9 derivatives of the given function f of x, right? We know what that is right here. But you're going to quickly see that that becomes very tedious. Even from the start, we'd have to have the quotient rule, and then the derivatives would grow in complexity. But as we've seen before, what we can do instead is take advantage of the definition of Taylor polynomials. So this Taylor polynomial is presented to us centered at 0. So what we can do is try to look for like terms. So we know that t sub 11 of x, if we're talking about being centered at 0, well, that should be the sum from k equals 0 to 11 of the kth derivative of f at 0 divided by k factorial times x minus 0 to the k. So the coefficient of x to the 9th should be the 9th derivative evaluated at 0 divided by 9 factorial, right? So what I mean by that is looking at my definition of the Taylor polynomial, I can figure out what should sit in front of x minus 0 to the k, right? So if we are looking for the 9th derivative, what's significant from this is I should expect it to sit in front of x minus 0 to the 9th. What I can do is go to my series and find the x to the 9th term, or my polynomial, I should say. So the task here is to match coefficients. And what I mean here is match coefficients of x to the 9th. So what we do see as the coefficient of x to the 9th is negative 1 over 16. So negative 1 over 16 is the coefficient of x to the 9th. It should be the 9th derivative evaluated at 0 divided by 9 factorial. And what I want to isolate here is what sits up on this part here. So to isolate that, I'm going to multiply both sides by 9 factorial. And now I know that must have been the case that the 9th derivative evaluated at 0 was negative 9 factorial divided by 16. So notice that we can't use the polynomial to tell us what the 9th derivative as a function of x is, but I can find it specifically at the center 0. And by the same token, that was part A, same problem. If I said find now the 10th derivative of this function at 0, so we can use the same reason above where we want to match coefficients of x to the 10th. So what we look at here is kind of following the line above. It should be the 10th derivative of f at 0 divided by 10 factorial. That's what should go in front of x to the 10th if we're talking about a Taylor polynomial centered at 0. If we come back to our problem here, what you'll notice is that there is no x to the 10th. So it's as if I had a 0 times x to the 10th squeezed in between here. So anytime I'm missing a power of x, its coefficient is 0. So that means that we're matching 0 to this. And of course, if I multiply both sides by 10 factorial, then this just tells me that this must have been that the derivative of interest here was equal to 0. So we can extend all of that to our knowledge of Taylor series as well. So I, yet again, know for Taylor series that I know what the coefficient should be, right? This formula that I have in sigma notation here, if I send that upper limit on k up to infinity, that becomes a Taylor series. So in this instance, suppose I don't even know what f of x is. So f of x is a function that has Taylor series equal to the sum from k equals 0 to infinity, -1 to the k, k plus 1, x to the k, all divided by 2 to the k. So I don't know what f of x is, and I don't need to know what f of x is in order to answer the following questions. So first of all, we could answer the question, what is f of 0? So what we want to consider is that f of 0 is the constant term. So f of 0 is the constant term. So it shouldn't have any x attached to it. So in order to think about that, we could write out a few terms of this series. This would be when k is 0, we would get 1, let's see. When k is 0, we would get -1 to the 0 times 1 times x to the 0. So we would get 1 here. And then when k is 1, we would get a -1, and we would get 1 plus 1 divided by 2 to the 1, so that would also be 1, times x to the first. And the next term would be positive. We would get 2 plus 1 is 3 over 2 squared, so 3/4 x squared, and so on. So the constant term is 1, and that must mean, therefore, that the f of 0 is 1. If I ask now a question about a characteristic of f, maybe I'll put this here, is f of x increasing or decreasing at x equals 0? Now, in general, when we're talking about increasing or decreasing functions, we know that we can look at the sign of the derivative. And I would like to know here the sign of the first derivative. And again, we've already written out the terms, and the first derivative should come from the coefficient of x to the first power. So this is exactly what we talked about matching coefficients before. So from matching coefficients, I see that the coefficient of x to the first is -1. And for a Taylor series centered at 0, it should be the first derivative of f at 0 over 1 factorial. So we're getting that f prime of 0 is -1. And of course, what we care about is that that's negative. So that tells me, without even knowing what the function is, that f of x is decreasing at x equals 0. Again, thinking about what we do know and what we don't know, I don't know what it's doing away from 0. I only have information about the derivatives at x equals 0. And then finally, what is the 100th derivative of f at 0? Notice that I do not want to keep writing out all these terms until I get to the x to the 100th term. Instead, what I want to observe is kind of breaking this up into two pieces. When when I have x to the 100th, my interest is in what the coefficient would evaluate to. And so I noticed that I'm interested in k equals 100. So coefficient of x to the 100, we're trying to match those. And when we look at our series there, when I plug in k equals 100, I'm going to get -1 raised to the 100th power times 100 plus 1 divided by 2 raised to the 100th. That is the coefficient of x to the 100th that I pulled from my sigma notation. What we know is for Taylor series, the coefficient, so Taylor series centered at 0, the coefficient of x to the 100th should be the 100th derivative evaluated at 0 divided by 100 factorial. So what I'm trying to get here is that I want to isolate this part. So I want to solve for the 100th derivative at 0. And I'll point out a few things. -1 to the 100th, that's just going to be 1. And so I have here my 101 over 2 to the 100, but I'm going to multiply by the 100 factorial. So in fact, if I wanted to simplify this, this is 101 factorial divided by 2 to the 100. So I don't even know what the function f of x is here, but simply having complete information about its Taylor series centered at 0 would allow me to find any derivative of that function evaluated at 0.